Welcome students. In this video we are going to learn the SN2 reaction, its kinetics and mechanism. Now consider the hydrolysis of methyl bromide by aqueous NaOH to yield methanol. So this is the structure of methyl bromide CH3Br. This OH minus is nucleophile and this OH minus replaces this bromine atom from the starting material and gives methanol as a product, and Br minus is the good leaving group. So the kinetic of the reaction shows that rate is directly proportional to the concentration of methyl bromide and concentration of nucleophile. That means here OH minus is a nucleophile and methyl bromide is our starting material. So therefore the rate is equal to K2 into concentration of methyl bromide, which is substrate, and the concentration of nucleophile OH minus. So here K2 is the second order rate constant. So therefore this SN2 reaction depends on the concentration of substrate as well as on the concentration of nucleophile. So this is second order rate constant SN2 reaction. Now the proposed mechanism for this SN2 is given by Ingold. So Ingold, who studied the mechanism of this reaction, proposed that the nucleophile OH minus attacks the carbon atom from backside of the CBr bond, and the formation of COH bond and breaking of CBr bond take place simultaneously. So bond making and bond forming process are concerted. So the energy released in the COH bond formation is utilized for the breaking of CBr bond. Here you can see the mechanism. So OH minus attacks from the backside of the CBr bond, and here CBr bond breaking take place. This is the transition state of SN2 mechanism. So here partial COH bond formation is there and partial CBr bond for bond breaking process is present, and here you can see the final product. So OH minus attacks from the break side and from front side the CBr bond breaking take place. So here you will get the product of that is methanol. So Br minus is good leaving group, and also you can see that in starting material this carbon atom is having sp3 hybridization, and then in transition state that sp3 hybridization is changes to sp2 hybridization, and then again this transition state collapses into sp3 hybridized carbon atom. So the question is, why backside attack? The nucleophile OH minus approaches from the backside of CBr bond because there is a minimum steric interactions and requires minimum energy. If OH approaches from the front side, that is from the same side where CBr bond departs, there will be a lot of steric interactions as well as dipole repulsion, as both of them have negative charge, and this approach will be high energetic. So here you can see this OH minus attacks from the backside. So there is a less or minimum steric interactions between Br and OH minus, and also there is an absence of dipole repulsion. So this is less crowded backside attack. If OH minus attacks from the front side, so this OH minus and Br minus are from the same side, so they creates a dipole repulsion. So they create a dipole repulsion, and this is more crowded and high energetic. Therefore nucleophile approaches from the backside of this CBr bond. Now energy profile diagram and transition state. This is energy profile diagram for SN2 reaction. So here nucleophile attacks to the starting material, then transition state form, and this transition state collapses into the formation of products. So here you can see the energy of activation required for the formation of transition state. Okay, so this is energy profile diagram of SN2 reaction. This is the transition state, which is high energetic, and here you can see that transition state. So in the transition state, the carbon atom is bonded to 5 groups. The OH group, Br groups are located as far apart as possible. The 3 hydrogens and carbon, these are lie in the same plane or in single plane, and all bond angles being 120 degree. If you see the transition state, so this hydrogen and this hydrogen, they are 120 degree apart from each other. This is sp2 hybridization for this carbon atom, and the nucleophile and this leaving group are in the plane which is perpendicular to these 3 hydrogen atoms. That means if you see this carbon atom and these 3 hydrogen in a single plane which is present on screen. So suppose this OH minus attacks from back side of the screen, and from some front side this CBr bond breaking take place. That means they are perpendicular to the screen. The transition state possesses high energy. You can see here in the energy profile diagram, transition state is having high energy and it breaks into the product. During the formation of transition state, there is a change in hybridization of carbon atom from sp3 to sp2, and when transition state collapses into the product, the hybridization changes back to sp2 to sp3. Now next point is stereochemistry of SN2 reaction. As the attack of nucleophile OH minus is from the opposite side of leaving group, in the final stage, inversion of molecule take place. So if the substrate contain chiral carbon atom bearing halogen atom, then the molecule always produce inverted product. Example is R-2-bromooctane is allowed to react with sodium hydroxide under the condition where second order kinetics is followed, gives S plus 2-octanol. So here you can see that this R-2-bromooctane is converted into S plus 2-octanol. So here R is converted into S and minus. This optical rotation is also changes to plus. So there is inversion take place. So there is inversion of configuration take place. So here you can see the structure reaction. So this carbon atom is chiral. So this is 2-bromooctane and the configuration is R. This is R-2-bromooctane. So OH minus attacks from the back side of this chiral carbon atom, and from front side this bromine departs. So here you can see the transition state. So all these 3 groups are in the single plane, and these OH and Br, they are perpendicular to the plane, and then this transition state collapse into the product, that is octanol, and the configuration of this is S. So this is S plus 2-octanol, and you can see the optical rotation. This R-2-bromooctane has optical rotation minus 39.6 degree, and the product is found as plus 10.3 degree. That means here R configuration it changes to S. That means there is a complete inversion take place in SN2 reaction. So a reaction that yield a product whose configuration is opposite to that of reactant is said to proceed with inversion of configuration. So here reactant and product have opposite configurations, therefore this is known as inversion of configuration. Now there are some experimental evidences present for the inversion of configuration. So in order to prove the inversion of configuration, a reaction sequence is carried out in such a way that optically active reactant is converted into its enantiomer. Here you can see the reaction sequence. R1-phenyl-2-propanol having configuration plus 33 degree is on reaction with tosylate chloride in presence of pyridine gives this tosylate derivative whose optical rotation is still plus 31 degree. And then here you can see the SN2 reaction with sodium acetate. So this intermediate on reaction with sodium acetate. So here sodium acetate is a nucleophile. So this acetate ion attack from the backside of this tosylate group, and this OCO bond breaking take place. So this is SN2 mechanism. So here you can see the change in optical rotation. So here optical rotation changes to -7 degree. So here +31 is present, and in third step you can see that there is change in configuration. So here inversion of configuration take place, and then if this intermediate undergoes hydrolysis with in presence of water, gives S1-phenyl 2-propanol as a product whose configuration is exactly opposite to that of reactant. So this is having -33 degree optical rotation, and these two are mirror images of each other. These are enantiomers of each other, reactant and product. So this clearly indicates that in SN2 mechanism there is inversion of configuration take place. Then second evidence is when R2 iodooctane is reacted with radioactive 128I- under SN2 conditions, it was observed that the product formed was the racemic mixture, and the rate of racemization was twice the rate of exchange of iodine. So the rate of racemization is 5.8 into 10 raised to -5, and the rate of iodine exchange is 3 into 10 raised to -5 at 30 degrees Celsius. So here is the reaction. This is 2-iodooctane. Then this radioactive iodine attacks from the backside of the Ci bond. This is SN2 mechanism. So transition state is formed, and then this transition state is collapses into the product, where you can see the radioactive iodine is now attached to this carbon atom. So this is S2 iodooctane is formed. So in this SN2 reaction, iodide is replaced by labeled iodide 128, and when one of its dextroisomer undergoes SN2 reaction, its enantiomer is produced, which pairs with unreacted plus isomer to form racemic mixture. So here you can see this is plus isomer and this is minus isomer. So when one isomer is converted into minus, so here this minus pair with unreacted plus and form racemic mixture. So thus when one molecule undergoes SN2 reaction, get cancels the optical activity of two molecules. Therefore the rate of racemization is twice the rate of exchange of iodine. That means all these evidences proves that in SN2 reaction there is an inversion of configuration take place if that substrate is having chiral center. Thank you.